Well, hi again. This is Bob. I can't tell you the number of times I've tried to record the lessons on 5.4. I keep getting a disconnect, and I'm not sure it's because of the Blackboard system or just the fact that I'm using a different internet service provider right now. So I'm going to try again, and I had originally planned on doing 5.4 in 2 lessons, but if it happens to, I may just break this down into more than 2 lessons because I've had, on occasion, lost my signal and had to start all over again. So, on the other hand, you may never even see this particular recording. If it goes south again, I'll just find myself another internet connection. Anyway, what we're going to look at first, we've got 4 new distributions. I would consider this topic sort of enrichment because these aren't the main distributions that we will use, but they're important, and many of you will probably take other statistics classes, and having some background in these, or at least being aware of these distributions, could be very helpful. And the first one we're going to take a look at is called the multinomial distribution. And if you remember that the binomial distribution dealt with 2 outcomes, then the idea of the multinomial distribution is it deals with more than 2 outcomes. And on the bottom of 289, again, I'm assuming that you've read through the material closely, but they give us a couple of situations there. One of the situations is, let's say you're taking a questionnaire, and instead of just a yes or no type answer, what if they have like yes or no opinion? So there you would have like 3 choices or outcomes. And then one that's even a little more dramatic, it would be, let's say that a person or a couple could choose from 5 Friday night activities. And they give some examples such as a movie or dinner or baseball game or play or party. Okay, well, each of these have more than 2 possibilities, and so we need another type of distribution to figure out probabilities, and that's why when they introduced the multinomial distribution. And the top of 290, I'll just go through these. I'm still crossing my fingers that I don't lose my connection. In order for us to use this, there must be a fixed number of trials. That was also true for the binomial distribution. Each trial has a specific, but not necessarily the same, number of outcomes. The trials are independent of each other, and the probability of a particular outcome remains the same. So there's a lot of similarities between the binomial distribution and the multinomial distribution. In fact, we can even consider, and they tell us this later, that the binomial distribution is a special situation or case of the multinomial distribution. And why don't we just take a look at this formula for multinomial distribution right now. There's a lot of similarities. Notice that it starts off like our binomial with n factorial on top. Then in our denominator we have like x. That's our first event, if you will, and then it's a factorial, of course, and then we have like x2 factorial, and then we have, these are being multiplied, by the way, the third outcome factorial. Then it goes out to x sub k. Okay, so those are the different outcomes, if you will. And then they give us the probability of each one of these outcomes, like the probability of 1 and the probability of outcome 2, and then they go out to probability of that last outcome, which they're calling k. And notice that the exponents, this looks familiar, are the same as the outcomes that were desired. Now, once we use this formula, it may look a little intimidating now, but I think it goes pretty straightforward. Anyway, check this out. The outcomes, if you notice, in other words, like our x sub 1 and our x sub 2 and our x sub 3 out to x sub k, there's supposed to be 3 dashes here, equals n. Okay, that's familiar from the binomial distribution. And notice that all these probabilities add up to 1, which we've seen before also. So probability of 1 plus probability of event 1 and event 2, and probability to that last event k, all add up to 1. So there are, as we would expect, some similarities when we use this formula here. So why don't we just take a look at this first example here. It deals with herbicides, and we have some, and the nice thing about this is they're going to give us the probabilities, and then they're going to give us the total number that we sample, and then they'll break that down. It's all done respectively with the way that the N is going to be composed for each outcome. So let's just get some information on example 525. Okay, so the first thing is 65% of individuals use herbicides for commercial purposes. I'll just jot that down. And I'll use COMM for commercial. 27% use herbicides for agricultural purposes. I'll write AG for that. And that leaves 8% for home and garden. I'll write HG for home garden. So right away we noticed that the 3 probabilities that they give us add to 1, so we're fine there. So here's what we're going to do. They're going to sample 5 people, and of the 5 people sampled, remember this all goes in order, we want to know the probability that 5 people that use herbicides, find the probability that 3 use them for commercial purposes. So here's what I'm going to do. I'm going to put a little 3 here just as a reminder. And notice that they started off by giving us the probability of commercial, and now we've identified 3 as our number selected of the 5. And then that leaves 1 for commercial and 1 for agricultural. So this is just little notes to me. Okay, the next thing we want to do is we want to set this thing up so it would be the probability of X given those circumstances there. Well, we have 5 factorial on top, which we would expect. And then notice of the 5 factorial on top, the people using it commercial were 3, so this becomes 3 factorial, times the people using agriculture was supposed to be 1, so that becomes 1 factorial, times the number of people using it for home and garden, that becomes 1 factorial. Okay, and the 3 and the 1 and the 1 on the denominator add to 5, and then of course our exponents are going to have to add to 5 in the respective order that they've given us. So again, I'm going to write 0.65, that was our first probability. Then I'm going to write 0.27 as our second probability. And then I'm going to write 0.08 for our third probability. Okay, and these respective the exponents here will be respectively 3, 1, and 1. Okay, now the answer, which I'm have worked this out on my own beforehand, and it came out correct with the book, is 0.119, or about 11.9% that the breakdown would be as they described. Okay, and there's a little note at the end of the bottom, directly below example 525. It says, note that the multinomial distribution can be used even though replacement is not done, provided that we have a small sample in comparison with the population. So a lot of people use herbicides, and we only took a selection of 5 from that large population. Okay, and we did not, it's assumed, do replacement on this question. Well, I'm going to cross my fingers one more time and hope I can get lucky before and not lose my signal on doing that coffee shop problem. This is example 526. When I really am crossing my fingers here because I had planned to do 2 lessons here, but I'm and just going to stop at 1. Anyway, we have, the next one's about coffee shop customers. Got a small airport coffee shop manager, and he had the probabilities of the number of cups of coffee. And this is just for me. You can maybe do it your own way. But this coffee shop manager kept records over a long period of time and found out that the probabilities that a person orders 0, 1, 2, or 3 cups of coffee are respectively 0.3 for 0 cups of coffee, 0.5 for 1 cup of coffee. This is just the way I set up a little table as a reminder. 15% or 0.15 for 2 cups of coffee. And then finally, a 5% chance that somebody would order 3 cups of coffee. Obviously, in this situation, many coffee shops give you a refill, but this looks like you have to purchase again. So here's the last thing we're going to do. We're going to sample 8 customers, okay? And of the 8 customers, and remember, it's all respective here. If 8 customers enter the shop, find the probability that 2 will not order coffee. So I'm just going to write 2 here. Again, that's for me. You can organize your data any way you want. 2 will purchase something other than coffee. 4 will purchase 1 cup of coffee. And 4 will purchase 1 cup of coffee. 1 will purchase 2 cups, and 1 will purchase 3 cups. Okay, so I've got some kind of a little table there that's just going to be helpful for me. And we're going to sample 8 people, and of course, that's not a very big sample out of the large population at an airport that orders coffee. So let's find out what the probability would be. And again, I am really crossing my fingers I don't lose my connection here. It would be 8 factorial on top. Now we're going to break this 8 factorial into, actually I think what I'll do is I'll go ahead and put my, it doesn't matter, but I think this time I'll go ahead and put my probabilities next. 0.3, 0.5, 0.15, and 0.05. And you can follow along in the book, of course, on this. And now, let's see, we wanted 2 people to order 0 cups of coffee, and we wanted 4 people to order 1 cup of coffee, and it was 1 person for 2 cups times 1 person for 3 cups. So if you notice there, I've got my setup. The only thing I haven't done is put the exponents. And remember that in the order that I've listed the people that order their coffee, none, 2, 3, those become the exponents of the probabilities for each of those events, 4, 1, and 1. So if you look up on the top of page 291, you'll see that my setup is exactly like the books. And again, I worked this out ahead of time. They tell us that that probability of X is about equal to 0.354, or excuse me, 0.354, or let's say around 4%. Okay, and again, the population's large and the sample is small. Well, I'll ask you to take a look at question 5 or example 527, and notice they tell us again, just to sort of reinforce the idea, the multinomial distribution is similar to the binomial distribution, but has the advantage of allowing you to compute probabilities when there are more than 2 outcomes for each trial. That is, the multinomial distribution is a general distribution, and the binomial distribution is a special case of the multinomial distribution. And you may recall I mentioned that at the beginning of this lesson. Okay, well, I'm just hoping that not only did it doesn't look like I lost my internet connection, but I'm crossing my fingers that this actually works. So be back shortly with some thoughts on the Poisson distribution. Thank you.